as an organ. What's the target organ that I just mentioned? The uterus. How about target cell? We talked about the uterus contracting. So what's the target cell? Smooth muscle. Yeah. As a layer, it's called the myometrium, the muscle layer of the uterus. So it's getting those muscle cells to contract with more force. Well, how do you do that? How do you get a muscle cell to contract at all? What has to be released as the intracellular trigger? Calcium. Calcium. That's the intracellular trigger, right? Well, if you release more calcium, what do you get? A stronger contraction. So that's what oxytocin is doing. It's increasing intracellular calcium concentration for stronger and stronger contraction. And that's what I put on the study guide. Now I also added in parentheses, prefaced by FYI, that it's working through the PIP2 calcium second messenger pathway. But since I did put FYI, I won't test you on that bit of information. Right? Anything marked FYI, not going to be on the exam. So what's the action? We've got the stimulus, we've got the target. What's the hormone action? What happens to the uterus? Right? Uterine contractions for childbirth or parturition. There's another target. Smooth muscle cells. They're actually myoepithelial cells, sort of a hybrid cell that is capable of contracting in the breasts. And these myoepithelial cells surround the secretory units that produce milk. So the milk goes into a system of ducts, and then surrounding the duct, in the wall of the duct, you have smooth muscle cells. Surrounding the big cluster of secretory cells, you have myoepithelial cells. And all of those cells start contracting. So those secretory units are squeezing, the ducts are squeezing, and it forces all that milk through the duct system and out of the nipple. It's called milk letdown or milk ejection. So that's the hormone action. Right? We're targeting essentially muscle cells. And in this case, it's squeezing on the duct system to eject milk. This is a pretty good concept map. It's a good starting point. There's certainly a lot you could add to it. But like the one I made on the Excel spreadsheet that I showed you, we're organizing it with the hypothalamus at the top, showing how it controls the pituitary. And then from there, all the hormones coming from the pituitary, and then what they target. So you've got a lot of 3 hormone pathways here, and a couple 2 hormone pathways that I'll point out later. Right, so how about the one we just covered? Hypothalamus contains paraventricular nuclei, right, which produce oxytocin. It goes down these really long axons that go all the way through the infundibulum and end right here in the neurohypophysis. And then that's where the oxytocin enters circulation. And then from there, targets the uterus. And in the male, it does target the prostate. And then what are they leaving out here? What's the other target we talked about? For milk ejection. Yeah, the breasts. Supraoptic nuclei, SON. They produce mainly ADH. ADH has many targets, including the kidneys. The kidneys are producing filtrate all the time, right, as they filter the blood. So basically, you're taking the plasma, you're pushing it across the capillary wall. It enters a system of tubules, right? So we can call it filtrate. And the filtrate passes down the system of tubules. And if we don't take the water or the substances dissolved in that filtrate out, what happens to it? Where's the end of that system of tubules? The toilet. Right? The tubules empty into the calyces, into the pelvic, renal pelvis, into the ureters, into the bladder, out the urethra, and into the toilet, preferably. In other words, it's lost. It's excreted. It's urine. It's gone. Well, you produce 180 liters of filtrate each day. Most of us don't pee 180 liters each day. It's a lot of peeing. You'd just be on the toilet all day. We reabsorb 99+% of that filtrate. So that it's more like a liter of urine each day, not 180 liters. So antidiuretic hormone increases the amount of filtrate or water that we bring back into the body so that we lose less in the urine. So diuresis is water loss. This is antidiuretic hormone. It prevents water loss. It makes sure that we reabsorb more of that filtrate. Keep it in the body. We're going to talk a lot more about this hormone when we get to the urinary system, so I'm keeping it brief for now. At this point, just know stimulus or stimuli include low blood pressure and high blood osmolarity. And we have receptors for both. We have baroreceptors for pressure. We have osmoreceptors for osmolarity. And it turns out that the osmoreceptors are in the hypothalamus. And in turn, those osmoreceptors communicate with the supraoptic nuclei. If osmolarity is too high, would you want to excrete more water, or would you want to reabsorb more water and put it back into the bloodstream if your osmolarity is high? Well, there's two ways to bring down a high osmolarity. One, you could take some of those solutes out, so it's not so concentrated. That would bring down the osmolarity. But if you can't pull the solutes out, what could you do to dilute the concentration of solutes? So do you want more antidiuretic hormone or less if you have high blood osmolarity? More. Yep. So you're putting more fluid, more water back into the bloodstream to dilute the high concentration of solutes. So high osmolarity is a very strong stimulus for the secretion of ADH. If you have low blood pressure, do you want to pee out more water or conserve and reabsorb more water? If you have low blood pressure, you want to reabsorb more water because the more water you put into the blood vessels, the higher the pressure. Right? That's why when you're dehydrated, that can cause blood pressure to drop, right? Because your volume's going down. But if we can increase the volume, pressure goes up. So sure enough, low blood pressure is another stimulus for the release of ADH. The more ADH you have, the more water you reabsorb, the less you pee out. So urine output goes down. As ADH goes up, urine output goes down. Make sense? Mm-hmm. So ADH fixes both problems, a low blood pressure and a high blood osmolarity. How it does it, that's really what I want to save for urinary system lectures. Later, and this is in the little box marked FYI, I'll mention it, but again, if it doesn't make sense to you, don't worry about it. Not going to test you on it yet. Later in the urinary system, we'll cover ADH in more detail. You'll see that stimuli include not only high osmolarity and low blood pressure, but also an increase in levels of another hormone called Ang2, which is short for angiotensin 2. Ang2 is going to help ADH increase blood pressure when it's too low. As far as the actions of ADH, what it's actually doing to raise blood pressure, I've more or less mentioned it. It increases water reabsorption in the kidneys to increase blood volume, which increases blood pressure. The other thing it does, and the reason why ADH has a second name, vasopressin, it targets vessels, vaso, and constricts them to increase pressure, pressin, right? Vasopressin, vessels, pressure. It's a very powerful constrictor. Ang2 is also a powerful constrictor, so again, those two hormones often work together. So when you're describing the relationship between the hypothalamus and the posterior pituitary, would you say that's a vascular relationship? We're not talking function, we're talking anatomy. or a neural relationship, a vascular connection or a neural connection? It's a neural connection, specifically the tract, the hypothalamic hypophyseal tract. That's really what connects the two. Now we're moving on to the hypothalamus and the anterior pituitary. Now the hypothalamus is connected to the anterior pituitary through blood vessels. Vascular connection. These neurons are a bit short. The axon terminals are not way down here where the cells are that we need to control. They end up here. But we need to get the hormones, the releasing and inhibiting hormones that are made here in the ventral hypothalamic nucleus. We need to get them down here. So what we have to do is put them into a capillary bed. Capillaries empty into veins. But what's weird here, typically veins go to the heart. Well, these veins don't. They go into another capillary bed. So when blood goes from a capillary bed through veins into another capillary bed, it's called a portal system. And there's two portal systems we'll cover this semester. Hepatic portal system. And where's that one going to be found? Liver, hepatic. And this one, which is hypophyseal portal system, the pituitary. So that's how we get these hormones down here in the anterior pituitary. They go into that portal system. Capillaries, through veins, to another set of capillaries. The first set is the primary capillary plexus, and then the second set is the secondary capillary plexus. So you could say the releasing and inhibiting hormones enter the primary and then exit the secondary to reach the target cells. This group of releasing and inhibiting hormones, which are all amino acid derivatives, they can also be called regulatory hormones. So the hormones are produced in the cell bodies of the VHN, travel down the axons, exit the axon terminals, enter the primary capillary plexus, pass through the portal veins into the secondary capillary plexus, where they exit and reach the target cells, which are the acidophils and the basophils, or more specifically, the corticotropes, the thyrotropes, the gonadotropes, the mammotropes, the somatotropes. So I'm listing all of the regulatory hormones secreted from the VHN, and they're bold: TRH, CRH, GnRH, GHRH, GHIH, PRH, PIH. Those stand for thyrotropin-releasing hormone, corticotropin-releasing hormone, gonadotropin-releasing hormone, growth hormone-releasing hormone, growth hormone-inhibiting hormone, prolactin-releasing hormone, prolactin-inhibiting hormone. And then underneath, I'm reminding you of what hormone they regulate. So in the 3-hormone pathway, or 2-hormone pathway in 2 cases, these all represent hormone 1. So below, when I say TRH regulates TSH, I'm indicating what hormone 2 is, right? Which hormones are connected. So TRH is connected to TSH. CRH is connected to ACTH, and so on. Okay, so we're starting to put the whole 3-hormone pathway together. So that brings us to the adenohypophysis, right? It contains the cells that are being targeted by all of those releasing and inhibiting hormones. The hormones released from the adenohypophysis are TSH, ACTH, LH and FSH, growth hormone, and prolactin. Okay. How about the alternate names? TSH is also called thyrotropin, ACTH, corticotropin, LH and FSH together as a group. They are the gonadotropins. Growth hormone, somatotropin, prolactin, mammotropin or lactotropin. Now, there's a good reason we shouldn't call prolactin mammotropin or lactotropin. Those names imply tropic, that it's a tropic hormone, right?
Mm-hmm.
It's not. Prolactin is not a tropic hormone.
It comes from a trope.
The cells that produce it, you can call mammotropes or lactotropes. That's fine. But I wouldn't call prolactin itself mammotropin or lactotropin simply because it's not a tropic hormone. And that name implies that it is.
Do those cells then secrete other tropic hormones? That's why they're called trope.
So now we're going through and listing all the cell names. Thyrotrope cells, corticotrope cells, gonadotrope cells, lactotrope cells, somatotrope cells. And reminding you what it is that they secrete. And I'm giving you both names. The more common name first, and then the tropin version in parentheses. And notice, I gave you thyrotropin for TSH, corticotropin for ACTH, gonadotropins for LH-FSH, somatotropin for GH, but notice for prolactin I didn't put lactotropin or mammotropin. Right? I would not use those terms. It is not a tropic hormone. So here's another concept map. Starts with hormone 1 at the top, coming from the hypothalamus, showing you the hormone 2 that it regulates, coming from the adenohypophysis, and in turn, what peripheral endocrine tissue or gland hormone 2 targets, right, to regulate secretion of hormone 3. So 3 hormone pathway. GnRH, gonadotropins, gonadal hormones. Corticotropin releasing hormone, corticotropin, cortisol. Thyrotropin releasing hormone, thyrotropin, thyroid hormone. When it comes to prolactin, 2 hormone pathway, not 3. And again, prolactin is not tropic. So it stops at 2. Prolactin releasing hormone is 1. Prolactin is 2. Non-tropic. There is no 3. Growth hormone is part of both, a 2 hormone pathway and a 3 hormone pathway. It has both tropic and non-tropic effects. As a 3 hormone pathway, growth hormone releasing hormone stimulates secretion of growth hormone. Growth hormone targets the liver, stimulating secretion of somatomedins, also called insulin-like growth factors, IGFs. Somatomedins, in turn, promote growth of tissues, including soft tissues like muscle, connective, but also bone. So here's what's interesting about growth hormone. It is called growth hormone. We used to think it was specifically responsible for binding to receptors on these target cells and stimulating growth. And we later found that's not the case. Growth hormone exerts its growth effects indirectly. There's a mediator. There's something between growth hormone and the target cell that's being stimulated to grow. So who's the middleman? Who's the mediator? Somatomedins. Somatomedins. I think that's the better name. In most books, they refer to it as IGFs, insulin-like growth factors. And that's fine. That name does remind you that it has some insulin-like effects in terms of promoting growth. Now, growth hormone by itself, as a non-tropic hormone, can target tissues to do things other than stimulate growth, like target adipose to stimulate lipolysis. Make sense? Has tropic effects, has non-tropic effects. It's part of both a 3 hormone pathway as a tropic hormone, but also part of a 2-hormone pathway where it does not have tropic effects. So what are the 2 examples of 2-hormone pathways? Growth hormone and prolactin. And which one has both, is part of both a 3 and a 2-hormone pathway? Growth hormone. So here they're focusing just on the 2-hormone pathway of prolactin. Here they're showing you both growth hormone as part of a 2-hormone pathway with these target tissues, where it has metabolic effects other than growth, but also growth hormone as a 3-hormone pathway where it stimulates the release of somatomedins, which do mediate all the growth effects. As far as the actions of prolactin, it targets the mammary glands, and it promotes prolactation, milk production. Prolactin stimulates milk production. What regulates the secretion of prolactin? The same exact neuroendocrine reflex that regulates secretion of oxytocin. So I talked about one of 2 neuroendocrine reflexes, and that was the one involved in childbirth, where you stretch the cervix, signals go up to the hypothalamus, you release more oxytocin, stronger contraction, more stretch, so on. Oxytocin also targets the mammary glands, right, for milk letdown. Well, suckling is the stimulus for milk letdown, not stretch of the cervix. So 2 different inputs, both trigger a neuroendocrine reflex. So stretch of the cervix and the suckling reflex during breastfeeding. Right? Well, that suckling reflex during breastfeeding that sends signals into the hypothalamus results in the release of 2 hormones. Oxytocin's one, prolactin is the other. Right? So the mammatrope cells are stimulated by this neuroendocrine stretch reflex. As is the PVN, the cells that produce and secrete oxytocin. And sure enough, oxytocin and prolactin work together. Same general target, mammary gland. Which one is stimulating milk production for next time? Because we can't make it fast enough for the current feeding, right? The baby is suckling, the baby's feeding. Which one is stimulating production of more milk for the next feeding? Prolactin. Which one is allowing the milk that's already there to be let down? Oxytocin. It's sort of like filling up your car with gas while you're driving it. That would make sense, right? Never have to stop that way. So literally, as the baby is suckling and feeding right now, one hormone is helping to let down that milk, but the other one is stimulating production for the next feeding. And that's why when feeding is reduced, production goes down. So we'll pick it up with growth hormone next time. Too much to start right now.